remember to mute. If you guys do have questions throughout the presentation here, please put them in the chat box. I will do my best to catch them as we're going. If not, we'll certainly have time at the end to go over it. So thank you for coming. This is an ActiNav webinar. ActiNav is a new product released last year by Universal Robots. My name is Trevor O'Brien. I am the robotics product specialist for Applied Controls. My contact info is here if you need it for after the presentation and want to reach out and talk further. I'll also display this at the end as we're going through questions, so you guys have some time to write it down if needed. If you're not familiar with Applied Controls, we're located in Malvern, Pennsylvania, and have a couple other sites in Maryland and in York, Pennsylvania. But we're employee-owned. We're an automation distributor. We take pride in educating our customers and supporting local manufacturers and bringing them kind of the latest and greatest in technology. We have a wide offering, and you'll see some of that today. Here are some of the products that we do support. Top, of course, is Siemens and Cognex, SICK, Universal Robots, but of course we have many, many, many other partners. If you're interested in anything here, we can certainly talk about that after the presentation. Let's jump into it. ActiNav. Again, this is a Universal Robots product. This is a 3D bin picking solution, but it's different than probably other 3D bin picking solutions that you've seen, and we'll go into that today. So in a little bit more depth, what is it? In true Universal Robots fashion, it's easy to use. It's designed to be a complete solution that anybody can really get into. But it's also extremely reliable. Pretty high precision when it comes to 3D bin picking, knowing that parts are going to be randomly oriented. You're going to get about 0.1 to 0.5 millimeters of repeatability when it comes to picking and placing your parts out of the bin. It's also what makes it unique is it's autonomously controlled. What that means is the robot doesn't need to be programmed from waypoint to waypoint. We'll go through what the details of that mean today. But the idea is that you give it this space to work, and the algorithms and the program and the software control the motion. So you're not going through the tedious task of programming each and every waypoint. So once you have that environment taught, it figures out how to pick the parts out of the bin, place them in an oriented and precise way. It's really important for a lot of the processes that you'll look at to have your part in exact orientation, and that's exactly what this does. So you may be asking, why is that so much different than other solutions? Bin picking's been around for decades. How can it really be this different and easy? So going into a little bit more depth about why it's so different, first off, you may be intimidated by a 3D camera. You may have never used one before. Well, luckily with this system and software, you're not going to be spending hours programming a camera. There's only 2 vision parameters. They're fairly intuitive to understand. And when you're teaching parts in front of the camera, it's a really simple process of just putting the part into the camera and letting it do its work. You don't really need too much experience robot programming either. It's really broken down in a step-by-step way, easy to digest, teach by demonstration. You'll hear that a few times today. So even if you have no experience with the Universal Robot, you'll be all right programming in ActiNav software. And again, we'll go through some of the steps so you can see how easy it really is. And another note is that this does work exclusively with the E series of Universal Robots. So this is not a product for any other type of robot manufacturer, and it's not even a product for the CB series of robots. So all E series of Universal Robots is an exclusive product for. So let's take a look at the product a little bit closer. On the right-hand side here, let me pull up my laser pointer. You'll see there's 3 main components of the system. Starting at the top here is the 3D camera. Of course, you do want that above your bin. We have some specs for how far they need to be based on the size of the parts. Then, of course, you have your robot with your end effector of choice. This is certainly a variable that we'll have to look at based on certain parts, whether you're using vacuum or two-finger grips. And then, of course, the brains behind the operation is what they call the Autonomous Motion Module, or AMM for short. Essentially, it's a computer. It's doing all of the processing. It's running a lot of the software, but it is broadcasting it on the teach pendant, which we'll talk a little bit more later about. But again, this set of components here is going to give you the autonomous operation, so no tedious waypoint programming, teaching the environment around it. Where is the camera? Where is this stand? What is the gripper? How big is the gripper? You're teaching it all of those things, but it ultimately leads to a faster deployment and ease of use. So what I want to do now is go through a video introduction. I'm going to talk through this video. There's not really anything that you need to hear out of the video, but it's going to show the robot moving, using the product, showing you that autonomous motion, which I think is sometimes hard to grasp without seeing it, and just giving you some step-by-step on how it works. So I'm going to launch this now. Type something in the chat if you guys are having trouble seeing this video. So in this product, this is some conduit. You're seeing the robot picking it up with a vacuum gripper and placing it in a very specific way. All that motion too that you're seeing, again, is done by the autonomous motion module. And this is going to elaborate on how unique the motion is based on the part in the bin, based on what gripper you're using and what angle you're coming at it at, how you're going to place it into your fixture. But clearly all of that complication would be very tough to program yourself, right? A computer is finding the most optimal path. For a human to do that, it would take a long time. And that's where a lot of the time savings is coming from. And this theme of pick, path, and place is something that Universal wants you to really consider and think about. So benefits, of course, are higher machine uptime, collision-free motion. Once you've defined, a wall or an attribute there, it's never going to collide with it. Certainly having as many parts in a bin is a benefit, so you can continue to run without transferring bins or putting new parts in a bin. Look at a little bit of the programming here, and we'll go in more depth later in the slideshow. Those are the 6 major modules there. I'm going to show you how to teach a clearance object. We'll use that phrase a few times. A clearance object is essentially a no-fly zone or something that the software needs to avoid. You're simply moving the robot to those positions. The tool center point, the TCP, defines that point in space in which you're referencing. You did 2 points. That obviously creates a line, in this case a capsule, which they're going to have a radius of, cylinder. So same concept goes for the bin as well. You did the 3D sensor and you can do all those posts, but the bin, of course, needs to be taught. There's a specific module in the software for the bin itself. You want to have some pretty high precision with it, so it'll ask you for, I think, 4 points for each wall, and then the floor and the top of each wall. But all of it is done by teach by demonstration. You're moving the tool center point. Of course, a variety of grippers. That 45-degree angle is pretty helpful too, to go in that for a little bit. Just the geometry of getting into a bin and not colliding with those 3 wrists at the end of a robot. So you see a common theme between these grippers, and certainly would recommend that as much as possible. When teaching apart, yeah, so we're doing a pick and a place rule here. So when you're teaching apart, it's as simple as grabbing the part, putting it under the camera, and hitting the teach button. The software has the CAD models of the gripper and the parts. Those are prerequisites before any of this is going. But of course, if it knows that in the robot position, the camera then can do the rest and kind of put the math together. When you're doing place, same kind of concept. You put it exactly where you want it to go. You do a pre-place and a post-place so that it knows clearance when it approaches the place and the pick. But it's pretty straightforward. A few parameters you can mess with, but ultimately that's what it takes. So let's take a little bit closer look at the software, talking about how it's fast to deploy. So those are the pick rules and the place rules in the top left here. You, of course, can have a couple different pick and place options, right? That part that we saw, the conduit, has about 3 different pick positions: top, left side, right side. And based on how you pick all of those, you are going to probably want to place them uniquely. Again, all of that's done the same way by just bringing the part up to the 3D camera, hitting this teach button. The camera finds the part, you verify that it found it in the correct orientation, and you accept those values. You can, of course, modify them if you wish. If you see that the part maybe wasn't perfectly centered on the gripper when you placed it there in your hand, or maybe the camera didn't capture it, you can adjust those offsets so that it can pick it more accurately. As I mentioned before too, there are pre and post pick calibration points or pieces that you can adjust, parameters. So if you want to make sure you're 50 or 100 millimeters away from your part and come straight down at it, that's where you would do the pre-pick, and similar concept for the post-pick. We'll talk about the 6 defined workflows on the next slide. As you can see, this is all programmed on Polyscope, right? None of this needs a third-party computer to kind of remote into it or anything. It's all done right here. And that autonomous motion module does help with this quite a bit. You may imagine, at least I did when I first was introduced to this, that maybe Polyscope would run pretty slow. There's a lot of processing power here. And that wasn't the case. The AMM really did do a lot of this processing, and it was a very smooth experience on the Teach Pendant. And it works out great because you're already going to be there configuring, everything you need for your robot. Why not do it with all your bin picking stuff too? It works out quite well. And then another example of kind of fast to deploy or easy to use, again, thinking about how many lines of code this would be if you had to program each individual path, throughout the process. The whole autonomous motion is really the key to all of this. And of course, the software package to interface with it just makes it leaps and bounds easier. All right, so let's go into those 6 modules. When you go to setup in your installation tab here, these are the 6 basic components that get set up for each part. Starting with system, this is just basic connectivity type stuff, making sure that the robot is connected to that AMM, the computer, which is also connected to the camera. Pretty straightforward process, but of course that needs to be done right, and you'll get a little green light when that's good. There's a calibration step for the 3D sensor. You are given a tool to attach to the end arm of the robot and put that into 8 or 10 different positions underneath the sensor. Pretty easy step-by-step process. And once that's calibrated and configured, you'll get a green light. It'll give you a score. So you know if you're doing well. If it's maybe not as high as you think it should, you go through it again, get a new score until you're satisfied. The next step is the tooling. So of course we need to know what is on the end of arm tool. Could be tons of different options when it comes to grippers. Most manufacturers will give you the CAD models that we will require for putting it in here. Once you have the CAD models uploaded, you do then need to create clearance shapes as well. So basically telling the system how wide or how close you can get to the gripper without colliding. You may decide that you want a little bit of buffer room, maybe give it another 50 or 100 millimeters of radius around the tooling so that you have enough clearance and feel comfortable with the pathing that it uses. Now keep in mind, the more clearance shapes that you have, or clearance objects that you have in this setup, the more processing time and maybe less options the robot has to move. So in order to be optimal when it comes to speed, you may want to try to keep those clearance shapes pretty close to the actual physical geometry of the tooling or your parts or bin. So that's going to go for all of these clearance shapes that we're talking about. So once you have the CAD model of the tool and the clearance shapes defined, that guy will go green and you're good. Environment is the next step, and honestly probably the longest step in my opinion, just because you really do want to take your time and make sure that everything that you don't want to hit has been covered, and clearly define any walls that are there, pillars like we saw, the camera of course, base of the robot. And there may be some things that take you by surprise, of course, because this computer is designing an optimal path. You may not be thinking about that path. Sometimes the robot will kind of go underneath of itself and around to get to your place position, and you may need to create some environment shapes to prevent that motion. So this is probably the most tedious piece. Again, it's not too bad. Once you get it set up and you want to program a new part, you don't have to ever do it again. All of these steps here, minus the part one, the bin including, once it's set, it's set. So for our demo robot in our lab, right, I don't have to go through all these steps if you send me some parts to go through. We're just going to teach the new part, get the CAD model loaded up, and go to programming the pick and place. But yeah, taking time with your environment is important and is going to be pretty helpful. Bin is the next one. You saw a little bit of that in the video, going against the walls, the top of the walls, the floor of the bin. All those clearance shapes are critical. And then of course the part, CAD model of the part, defining those clearance shapes as well. And you're off and good to go. So this is probably all combined more time consuming than the program itself. But in approximately 2 hours, if this is your first time going at it, you'll get through this and be pretty close to running. But these are the basic step process of setting up the ActiNav system. So let's go through a more in-depth example of kind of the teach by demonstration, which all of this is really the backbone of. You're going to do this many, many times throughout the process. So this is what happens when you click on the environment button on the last screen. It'll bring you to, your robot. And if you already have some shapes defined, you'll see that. If not, you're just going to see kind of a hanging robot. So you're going to have to program all of these pillars and the bin and such. But when you do that, you'll see the robot. If you have your tool configured, you'll see your tooling. And the idea is that you're going to move the robot to wherever your first object is. You're going to click what kind of shape you want to do. They have these planes, there's spheres, and essentially these cylinders. You click point 1, and then it's looking for you to click point 2. So you move the robot to the other position. You click point 2. And then you have a shape. It'll default, a name _1. You can change the name as you go through. It'll give you the positions of what those objects are at, and also give you some things to configure here with diameter and length. So if you wanted to make it larger diameter, you simply would type into that box, let's say 200, and there you go, changing the shape. You can do a little bit of validation to make sure that it's not hitting where you don't want it to, based on just visually seeing the end effector and where it is relative to whatever physical object you're trying to protect. And once you're good from there, you save and you move on. And obviously, you see that there are quite a bit of clearance shapes in this environment, which is important. But you hit your save, and you're good to go. So let's talk a little bit about overall benefits of using a system like this, now that we understand a little bit more about how it works, how the programming is set up, and the advantages there. Of course, labor is always a problem. Sometimes you have folks that aren't available because of sickness or illness, or maybe you're looking for folks to do more important tasks than just sit in front of a machine, feeding it apart every 10 seconds or what have you. So this is a great option for that. We'll talk a little bit more about some of the applications specifically, but of course, helping with labor is a big one. We have implemented one of these systems, and we've seen a fair ROI on that. So that's something to consider, moving labor from an operation or just getting consistent production. We'll share with you that story, and so you guys can see a firsthand account of what that ROI kind of feels like from a customer perspective. Deployment time is a big deal, of course, with something that can be easily programmed and configured. Again, that customer I was referencing, we did that in a day mostly. I mean, we were there for a second day to make sure it was running consistently and no bugs were kind of popping up, but the bulk of the work was done in one day. So when you can get that up and running in less than a week, I think that's pretty powerful. Low system integration risk. This is all from Universal Robots, which you guys know from a UR Plus side of things. They take integration and seamlessness, easy, fast deployment very seriously. This stuff is going to work. It's proven. It's not a science project. It's not taking a risk on all these parts communicating and having the right cables. It's going to work. So with low risk there, you can feel confident moving forward. Hopefully, you're going to see longer run times than maybe you do with manual operation, because you can change how big the bins are and how many parts are in them, so that you see continuous operation for longer. Of course, because you're using a universal robot, there's going to be high reliability with the system and hopefully maximizing your machine uptime. So here are a couple examples of applications. Machine tending is by far the #1 application we see with ActiNav. It just makes the most sense when you're talking about parts coming from a bin and needing to be worked. Most of the time, it's because they need to go into a machine and have another operation going. Not to say there's certainly other applications that bin handling is useful, but CNCing machining is on the top of the list for sure on the applications that we see ActiNav being used for. But of course, other supported workflows on the right, anything picking out of a bin, I'd love to talk to you about and learn more about the process. So let's talk about what it looks like to identify a good part, a good process, work in process station, something that maybe isn't going into a package right away or at a finishing step, something that's in between an intermediate step is a good place to start. Single part type in a bin is important for us. With a single bin, the robot can't pick out of 2 different bins of 2 different parts. Unfortunately, the software at this point in time is focused on just 1 part and 1 bin. Assembly operations are not great. Most of the time, the precision for assembly operations is higher than maybe placing into a self-centering chuck or a vise to help with the variation and just picking a part out of the bin and shifting around in the gripper and things like that. But feeding an existing robot assembly can be a good fit, because maybe the fixturing on that existing assembly has been defined well enough, and all that precision is worked with. Cycle time is certainly a common question people ask. 8 to 20 seconds is about the average. It's certainly difficult to predict that without doing an actual proof of concept. Every part is different. They lay in the bin differently. There are unique features from a 3D, geometry standpoint of every part, and the algorithm thinks about it and can differentiate them differently. So it's important for us to do a good proof of concept to give you a good cycle time, but something in the 8 to 20 seconds is certainly something to consider. It's not super fast. It's going to take some time, but I think once you see the benefits of having consistent performance, you'll find in the long run it's going to meet your performance expectations. One other thing to consider with the cycle time is regrip. Sometimes picking out of the bin is not the way that you want to place into your machine. Sometimes you need to pick, let's say, from an inside diameter, but you need to be on the outside diameter to place it onto a chuck in a machine. That's the situation we ran into with our customer, Precision Form, for the case study that we'll look at later, the customer that we implemented the ActiNav in last year. So they used a regrip station to make sure the parts are oriented the right way. So certainly something to consider. But yeah, you try to think about total throughput, right through breaks, through lunches. Maybe you're running off shifts with it, getting a little bit more juice out of it. So total throughput is sometimes a better way of thinking about how productive the system is rather than maybe a per hour basis. Part size is pretty critical, right? You don't want something super, super small. That's hard for the camera to identify. And you don't want something really big because maybe you can only get 25 of them in your bin and you're going to be changing bins out pretty often. Maybe it could work depending on the right circumstances, but I think generally speaking, you want this thing running for a few hours unattended to get the most out of it. So between 1 inch and 10 inches in size, 2 fists was used as an example. If it's kind of within that volume, that's probably a good part. Yeah, so there's some smaller and upper end sizes, but 1 and 10 inches, 2 fists is kind of a good rule of thumb. Some part types that have been used in the past: tubes, cups, 6 inches, 10 inches or so. Aspect ratio for tubes is important, and cylinders, just based on a vision standpoint and fitting in the bin and handling. Cast or machined parts, volumetric 6-sided parts. Another way to think about that is you normally need about 2 points of picking that the camera can identify left versus right, so that the robot has a couple different angles to come in at. Flat is always good, but thicker than 2 millimeters. There are 2 different sensors that these products come with in terms of size of parts that you can identify or distance away from the bin. So there is a medium sensor that is supposed to be mounted a little bit closer so it can see smaller parts, and the larger sensor about 5 millimeters in thickness for parts for that sensor. Things to avoid: screws, cable assembly, floppy parts, glass, it's hard to see, flexible parts, O-rings, things of that nature are not going to always lend itself to being identified as a rigid shape from a 3D camera is also being picked by a robot. Of course, as we saw, different end effector options: suction, magnetic fingers. You could do ID grips. OD grips work sometimes too. ID is generally better for picking inside of bins. As we talked about, there are 2 different sensor sizes here. So there are some dimensions for the 2 different sizes. Placement accuracy, 2 to 3 millimeters-ish. It all depends on kind of how well the parts are being seen. I've seen better than that. But regripping helps with that a lot, especially if you're trying to get pretty precise into a machine after the fact. Some parts can be placed directly without a regrip, though. Accuracy is a big variance depending on the part. We can also rescan to validate pick accuracy if it's critical. If you're going into a machine or a press or something that has a high chance of causing some damage if not done properly, we can verify the accuracy before placing. All right, so now we're going to look at the case study from Precision Form. This one does have sound. This one, turn up your volume a little bit if you need to, or at least be prepared that if it's too loud to turn it down real quick. But I'm going to start this up in a minute. I'm going to be quiet throughout the entire thing, and I'll talk to you at the end.
We've been manufacturing metal components in Lititz, Pennsylvania for over 30 years. We're a high to medium volume job shop or contract manufacturer, and we have lots of components where we make millions a year, and it's easy to justify the automation, but we also have lots of parts where we make maybe 5,000 a month, and it's hard to get an ROI to go out and customize a fully automated solution. We have 50 to 100 parts that we touch on a weekly basis for inspection or secondary processes. Some parts come off bulk operations and are jumbled together in large and deep bins. When we first started reviewing the bin picking solutions, we worked with a number of companies, and we often would send them parts and ask if they could pick them out of the bins. And the answers were always yes, but. And the buts were never acceptable to us. When Universal Robots and Applied Controls first reached out to us with this solution, we figured it was going to be the same as all the other bin picking solutions, where we send them the part and they give us the butt.
We sent the ActiNav team a number of parts, as well as CAD drawings and 3D models of the parts. And within 24 hours, they had sent us 3 different demo videos of them picking each of the parts that we were very impressed by.
We were actually shocked. This initial task for ActiNav was a very simple choice. We have a very old machine that we utilize to cut scallops in a part for firearms, and it takes one operator to sit there the whole time. And it requires a very precise placement to get it into the machine correctly. We were successful using a regrip station to give the robot that necessary angle to sort of have that touch and feel.
When we got the system here, it took maybe about a day's worth of work to actually set the system up and deploy it at the machine to a point where we could leave it alone and let it run. So in programming an ActiNav system, calibrating the sensor and defining the environment is very straightforward. You drag the robot arm to points where you want to place environment objects or calibration points. And once you define those points, the robot will navigate around them and avoid the environment. When you're choosing a part to pick, you feed the robot a CAD file, and it uses this information to determine the orientation that it needs to move the arm.
I can't be competitive at an international level in Lititz, Pennsylvania with one operator running one machine at a time. I have to have those operators running 3 or 4 machines, and this is a solution that allows me to use my legacy equipment to be competitive. 2 years ago, we bought a UR3, and the first implementation of that machine was to do inspection of a high-volume automotive part. In order for that to work, we actually have to hand load the tray, which is still faster than hand inspecting the part, but it definitely takes time and prevents that person from doing other important work. So being able to use ActiNav to present the bin as they come out of the parts washer, rather than having to unload and place them on a tray, is going to be hugely efficient. The ability to implement ActiNav on older equipment doesn't just have the obvious ROI of allowing a single operator to operate 4 machines. It allows you to rethink whether or not you have to replace that piece of equipment. At some point, those machines wear out and they stop producing 100% good parts. In the old reality, we would have to replace that machine. If we can implement a cobot ActiNav solution next to that machine and inspect out the 1% of bad parts, we've just taken $1 million piece of equipment, added a very inexpensive solution to it, and gotten another potentially 10 years out of that piece of equipment. We anticipate being able to use ActiNav for all of those other processes going forward.
When Universal Robots introduced ActiNav, we thought that was a game changer and a huge differentiator. We saw a specific need in our market where you've got a relatively low cost, low engineering product that competes with historically a 3D bin picking batch processing product that is extremely expensive. It goes across every industry, from automotive to food and beverage to material handling. It's a perfect fit for any type of unoriented presentation process.
There you have it. So at this point, I'm going to open the floor to some questions. I'm going to tab out here and see if I can see any questions that have been there. And here's my contact information. I'll leave that up for a second. Let's see. So it does look like we have a question here. So after watching a few videos on this, I noticed that scanning could probably be done a lot earlier in the process as soon as the robot gets out of the way to place an object. That way the path planning wouldn't be holding up as it appears to be when it sits at home position. Is this something configurable or is this something you're just working on? So two things. One, I do think that the scanning process could be optimized a bit. You'll notice though that most of the time it is trying to take images and get ahead of that path planning. But this is an earlier release, right? This product came out last year. I got to imagine this is something that UR is got on the roadmap of optimizing. We've already seen, I think, 2 software updates of the UR cap that have increased speeds dramatically each time. So yes, I do think that this is something that Universal is aware of and interested in improving. I don't see any other questions at this time. So if anybody has any thoughts, feel free to throw them out there now. Again, hopefully that video was pretty informative from a customer's perspective of why they were interested in the product, how it benefited them. You saw the use of regrip stations. There was actually 2 there for this circumstance because of the machine cycle time, being able to stage something coming out of the machine to be placed later on while the machine is running and not eating into the cycle time of the machine. Being able to pick an unfinished part, put it in there right after taking the finished part out, help them out in terms of cycle time. So yeah, hopefully you guys thought this was informative and helpful. Feel free to reach out via email or phone call, and we can certainly discuss your applications further. But I appreciate everybody's time today. Thank you for coming. And that's all I got. Oh, I got one other question. Here we go. How do you call the auxiliary box next to the robot that allowed the ActiNav system? Sorry, I don't know if I fully understand that. The auxiliary box meaning like the automation motion module, the AMM, the computer? So it's all kind of integrated. When you plug in the AMM to the robot and the go through the configuration process in the installation file, that option there tells you that everything's connected, everything's working. The UR cap and the software recognizes the AMM's connected, and it's all really done behind the scenes. So there isn't a ton of, connectivity type stuff in detail that you need to worry about. It just works. Hopefully that answered your question, but if not, feel free to clarify.